Hi, so this is Nasniewski. We're going through monoidal category theory. We're up to chapter 5, monoidal categories. We did last section, we did 5.1. What was 5.1? We talked about monoidal categories where the associativity was strict and the identity was strict. In other words, A tends to B tends to C is equal to A tends to B tends to C. Here we're going to weaken that, and we're going to talk about things called Cartesian categories. Okay, Cartesian categories are types of monoidal categories, and the idea is as follows. Whenever we saw in the beginning of last video, we listed off many times where we saw these things, monoidal categories, but a lot of times when we saw them, what we did was we saw the product. So for example, let's talk about set again. We're going to talk about S, we're going to talk about T, we're going to have S cross T. That's very nice. Now, one of the main things that we saw about this is that S cross T cross U, given three sets, okay, you can associate them. You can do the tensor product of these three sets in two different ways, okay, like this, and lo and behold, they're not equal. So in sets, using the product, it's not a strict monoidal category. Let's just see why. The typical element here is going to be a little s, a little t, a little u, okay, and a typical element here is going to be a little s, a little t, a little u, but here there's going to be this type of pairing. Okay, so that's a t. Okay, now these two, here's a typical element here, here's a very similar typical element, okay? You might just write this as S, little t, little u, but that doesn't come from taking the product of these elements, okay? So yes, they look very similar, they have similar names, they have similar elements here, but they're not equal, okay? They're isomorphic. Okay, so these two sets are going to be isomorphic, but they're not equal. So this is the beginning of something called coherence theory, where we start talking about things that the laws don't work out very nice, but they cohere, they get along, and we'll talk about that. Let's talk about another problem. Take the set S, multiply it with the one object set, okay? Well, these things, typical element in this is such an ordered pair, okay? As opposed to that, here's a typical element in this, S. Now, again, these two things are not equal. They're not equal. There's an isomorphism from this set to this set, but they're not equal, okay? So we're now beyond the level of talking about strict monoidal categories. Here, the associativity is not equal. And the unit is not equal. Okay, so, but let's just back up for a second and remember what we did in chapter 3, because in chapter 3 we talked a lot about categories with products. Those were the internal structures. So we talked a lot about it. And one of the things we saw was that if you have a product, you have a category A and it has a product, then that means that there's a way of getting that. But what it also means that we saw another thing is that if you have three elements in the category, then there's an isomorphism between them, okay? To be clear what we mean by an isomorphism, we mean here's a function, I'm sorry, let's write it another way. Here's a category, A cross A cross A. Okay. And I can take three elements of the category, okay, and I can do like this. Multiply the second and the third one, and then multiply the first one. Either way, you get an element here, or I could do it like this. multiply the first and second one, and then multiply that one with that. with that product. Okay, one of the things we saw in chapter 3 is that there is an isomorphism between these two natural transformations. So that's the same thing here. This is a component of that in this category. Okay, so we have to talk about such a natural isomorphism. So this is an isomorphism. Another thing we saw was if you take A, here's a functor like this, and here's a functor cross T. Pick a typical element here, cross it with the terminal object, you get another element here. Okay, and what we said is A cross T, T is the terminal object, is not equal to this, but there's an isomorphism. So that says something like that. We can call that lambda. Okay, great. So these were things we saw about, these are isomorphisms that we saw in chapter 3 when we were talking about categories with products. So now we can formulate exactly what we're talking about and make a formal definition of what do we mean by a Cartesian category. So, ready? Definition. A Cartesian category is a category, a bifunctor, a terminal object, okay, and it has let's bring in those natural transformations. Okay, so let's bring in those natural transformations. There is a natural transformation from this to this. Okay, it's usually called alpha, and it has a name. It's called a reassociator. Okay, let's just think about why it's called that. Okay, when you do parentheses, you're associating different elements. Okay, and when you're changing parentheses, when the parentheses are moving, it's reassociating. So A, B, and C was associated here, and you go over here and you say A and B are associated. So you're reassociating, and so you have a reassociator. Okay, and again, this is an isomorphism. Let's do another one. There's natural transformation from this functor to, let's call it the identity of A, okay, and that is called a right, okay, also natural transformation, written like that, yeah, and that's called, that's a Greek letter rho, a right unitor. Okay, unitor. I don't know if it's my names or other people's names. So this is the unit of the tensor product. So this is called a right unitor. And this is also another one called identity of A. And this is called a left unitor. Hold on, we're not finished. So let's go through this. A Cartesian category has a category, a bifunctor, a terminal object. I'm sorry, the bifunctor is the Cartesian product. Okay, that's the main thing. Okay, it has this reassociator, natural isomorphism. It has this reassociator, I'm sorry, this right unitor, this left unitor, there's one other thing. Okay, in chapter 3, we saw that when you have a product, you have A tensor B is isomorphic to B tensor A. Okay, and so we have this, okay, and I show you what it is called in the book. It's called, but we call it a braiding. Okay, and the way to think of it is, it's a tensor product, it's a map from the tensor product to, again, the tensor product, okay, but composed with BR. And what the hell's BR? BR is the map from A cross A to A cross A, BR, where you flip the elements. So here you're going to have A and B, here you're going to have B and A. So what this does is A times B, B times A. This is going to be a map from A times B. And again, it's a natural transformation. And we usually do that with the Greek letter gamma. So let's go through it again. Cartesian category. A Cartesian category is a category, a product with a product and an empty terminal object, okay, with 1, 2, 3, 4 natural isomorphisms, okay? Hold on. But these natural isomorphisms have to satisfy more relations, okay? Now, I'm not going to write what those relations are, and I don't do it in the book either, okay? Later on in section 5.3, we're going to show you what these relations are, okay? Because that's the most general form of it, and so just for pedagogical reasons, we're not going to bring it up here, we're going to bring it up there, and we're going to see it. And that's the beginning of coherence theory, monoidal category theory proper, not just category theory, but monoidal category theory. Okay, great. So again, there's 4 natural transformations, but they satisfy more complicated axioms, which we're not talking about here. Okay, great. So let's go through a ton of examples of Cartesian categories. Okay, and there's a lot. You ready? Set with the Cartesian product and the terminal object. That works. Okay. In section 1.4, we went through all these isomorphisms, and we showed how they're isomorphic. We're just doing it again. We saw them again in chapter 3, and we're doing them here. Okay. Topological spaces. You can also take the Cartesian product of 2 topological spaces. You can look at a one object topological space as the unit. Doesn't change anything. Let's talk about something else. Manifolds. Okay. Again, Cartesian product. Again, the terminal object. Okay. Again, for both of these, we don't talk about it, but the Cartesian product is not strictly associative. They satisfy these isomorphisms. Now, there's more to show here. Namely, in top, you have to show that the projection functions, okay, to make that product work are continuous. In manifolds, you have to make sure that the projection functions are not only continuous, they're smooth. Okay, we like that. We also have to show that the reassociators are continuous or smooth, etc., etc. It's not done in the book, but it's done in any nice topology book that cares about details. Okay, great. Let's talk about another one. Graphs. We saw that we could take the Cartesian product of graphs. Okay, and what's a one-object category? What's a one-object graph, I guess, is that? I'll just say that. Okay, so that's the category of the category of categories has a Cartesian product, and again, it's not strictly associative. It's associative up to this isomorphism, and the terminal object is the one-object category. So those are nice examples. Great. Now, some other examples. The category of semigroups, groups, monoids, all those algebraic structures that we talked about in the beginning of chapter 2 are all examples of it. Rings, etc., etc. All those have product structures. You could take them products. You could take the product of 2 of those structures. Okay, I'm blanking out on the first word. The magmas, etc., etc. But there's one place where it fails, and it's worth thinking about where it fails. Okay, so all those other algebraic structures all have products. They all work very nicely. Their products are not strictly associative. They're Cartesian products. Okay. However, fields fail, and the reason is worthy of spending time. Okay, if you have 2 fields, you could take the product of them. Hold on, you might try to take the product of them, and this makes sense, and you can see what the two fields, how the operations would work. So for example, you might have an element A and B. A is in one field, B is in another field, and you want to add it to another element, A prime, B prime. So that's very simple. You know how it works. It works pointwise or component-wise. So you're going to get A plus A prime, comma, B plus B prime. Very nice. Okay, you might want to multiply these things. Very nice. Times, you know what? Multiplication we'll just call dot. A prime, B prime. This is an element of a field. This is an element of a field. Both of these together are an element of a field. Both of these together are an element of a field. How's it defined? A dot A prime, comma, B dot B prime. Very nice. But we also need, in a field, you not only add, multiply, you subtract. By the way, subtraction works very nicely. Works out very good. Let's just do subtraction. Minus, minus, very nice. Nothing shocking. But you need inverses of this, okay? For every element, there has to be an inverse, except if it's a zero. But 1 second. What about this? What's going to be the inverse of this element? So the inverse of an arbitrary element, you might write as A minus 1, B minus 1. Okay, it has an inverse in here, it has an inverse in here. But what about this element, A comma 0? What's the inverse of this? So you might say it's A minus 1, 0 minus 1. Buzz. There is no inverse of 0. Okay, so fields are not really algebraic. They're something called essentially algebraic, but not really algebraic. The point is, it works good for plus, it works good for minus, it doesn't work good for division. Conclusion, fields, the category of fields does not have a well-defined product. Okay, great. Okay, some more examples. Now, let's just remember for a second. We talked about complex matrices last time, okay, and we showed that it had two operations, direct sum and tensor product or Kronecker product. Okay, now we're up to complex vector spaces. Okay, guess what? It's going to have two operations also. I'm going to call it like that. Let's do this operation first. Okay, you have a complex vector space V. You have a complex vector space W. We could take the direct product of them. Let's see what it's equal to. They're equal to, it's an algebraic structure. So just like we saw 2 seconds ago, they're equal to little v's and little w's, such that V is a member of V, W is a member of W, okay? And you add them the way you want. So let's go through this. These are vector spaces. It has a 0. What's the 0? 0 comma 0 is the 0. Okay? You can add them. Well, how do you add them? Very simple. V comma W plus V prime comma W prime equals V plus V prime comma W comma plus W prime. Where the plus is, this plus is in V, this plus is in W. Okay, so it works out very nicely. You have negations, etc., etc. So this works out very nicely. But, so that's the Cartesian product of two things, but you have, I'm sorry, that's the Cartesian product, but you have a lot of things to show. For example, you want to show that there are nice projection functions from V to W, from V plus W to W. So you know what this is. This takes V comma W, that's a typical element in here, and this projection goes to little v, and this projection goes to little w. So, and you have to show that this is a complex vector space, this is a complex vector space, and this is going to be a linear transformation. So you have to make sure that the projection functions are linear transformations. Okay, great. What else do you have to show? Well, you have to show that V plus 0, that's the trivial vector space, is isomorphic, we'll do it like that, to V. Not hard to show. Okay, next, V plus W is isomorphic, not equal, to W plus V. Not hard. Next, what else do you have to show? V plus W plus Z, what the hell, okay, is isomorphic, not equal to V plus W plus Z. Okay, and again, just think of a vector space. Oh, I'm sorry, this whole thing is finite dimensional vector spaces. Okay, this whole thing is talking about finite dimensional vector spaces, and think of a finite dimensional vector space as an algebraic structure. Okay, great. Okay, you know what? Since we're adding these finite dimensional vector spaces, I just want to show how it works in terms of basis. So if basis of V is, I don't know, B1, B2, B3, Bm, and basis of W is D1, D2, D3, Dn, then basis of V plus W is, watch this, so what are the basis elements? They're going to be pairs, something from here, something from here. So they're going to be B1, comma 0, comma, B2, comma 0, comma, dot, 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 Bm, comma 0, okay, comma, 0, comma, D1, 0, comma, D2, dot, 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 0, comma, Dn. Okay? Okay, so basically we add this basis plus this basis. So we can write this as follows. The dimension of V plus W, and by the way, these are all finite dimensional, so we have no problem. We're not talking about infinite dimensional things, is equal to the dimension of V plus the dimension of W. Can't get simpler than that. Okay, the other operation on finite dimensional complex vector spaces we're going to see later on at the end of chapter 5. So far we've only seen this one, direct product. Okay, and it behaves very nicely. Okay, let's look at some more examples of Cartesian categories. Okay. Okay, great. Let's talk about preorders. Okay, so take a preorder that doesn't have the antisymmetry. The antisymmetry is if P implies Q and Q implies P, then P is equal to Q. Okay, so preorder doesn't have that requirement. So we could talk about a product for a preorder, not a. We talked about partial order last time. This is a preorder, and we could talk about the 1. Okay. In this category, P1 and P2 and P3 are isomorphic but not equal to P1 and P2 and P3. Like that. Okay, and similarly, the same type of thing like that with the unit. So P1 and 1 is isomorphic, but not equal to P1. Okay, so that's pre-order. This again, just like in a partial order, is called a meet. So the product in a pre-order is called the meet of a category. Okay, I want to talk about a particular example of this, and this we saw at the end of chapter 4. Propositions, so this is all about logic. So we have the and, okay, and we have true. Okay, so that's an example of a pre-order like that. We don't assume that the and is associative, equal to its associativity. Okay, great. More examples. This is one of our first examples. Computable functions. Okay, let's just remember what that is. The objects are products of types, but we don't assume they're associative. We don't assume they're associative. And the morphisms are computable functions. So this is, again, a Cartesian category. Okay, great. Anything else? No, that's about it. Okay, great. Great. Now, one of the benefits of category theory is if you stand on your head and you turn around all the arrows, you get another whole world. Okay, so guess what we have? Definition, not a Cartesian category, but a cocartesian category. What's a cocartesian category? Well, it's a category with a coproduct. And instead of a terminal object, we have an initial object. Okay, and there's lots of examples of these things. But main thing is, we don't assume that the coproduct is associative either. So we're going to have, just like we had before, okay, but this time, instead of a product, we're dealing with a coproduct. And we have a reassociator, also called alpha. Okay, and we have a right unitor, and we have a left unitor, and we have a co-braiding. Okay, so same definition, and all these isomorphisms have to satisfy a larger class of axioms that we saw before, that we did not see before, but it's similar to the ones we saw before, but we're going to see them all in section 5.3. So again, those big axioms, which we're going to call coherence axioms, we'll see them a little bit later on. Great, so cocartesian categories, not only Cartesian categories, but cocartesian categories. These are categories with nice, not products, but coproducts. Okay, a ton of examples. Set, disjoint union, and the empty set, that forms a cocartesian category. Topological spaces, disjoint union, the empty category, that forms a cocartesian category. Manifolds, the empty manifold, that forms a cocartesian category. Again, there's a lot to show here, like inclusion maps are continuous or smooth, and the reassociators are, what's the word? They're continuous, they're smooth, etc., etc. Great. What else? The category of categories, you could take the disjoint union of two categories. I guess sometimes we write this like with this. Disjoint union of two categories. Take one category, take another category. That's a category. Okay. The unit here is the empty category. Same thing with graphs. You could take the disjoint union of two graphs, you get a graph. The empty graph is the unit there. Okay. Boolean functions. Okay, so this is a little bit more interesting and different. Okay. Okay, so let me tell you what these are. The objects are natural numbers, m and n. Okay, and a morphism from here to here is basically a Boolean function. So it's going to be a typical morphism from m to n is a Boolean function from 0, 1 to m. That's m bits to 0, 1 of n. Okay. Main point, if you have two such Boolean functions, then guess what you can do? You can take f plus g, okay, and that goes from 0, 1 to m plus m prime to 0, 1 to m n Nancy plus n prime. Okay, and the way to think of this is, look, this is going to have inputs an m plus m string. Okay, so what do you do? How does this new function work? These are functions from Boolean strings to Boolean strings. Well, the first part of the string is going to follow where f tells you, and the second part of the string is going to follow where g tells you. Okay, and we're going to use these much later on. But Boolean functions are a co-Cartesian category. Okay, it doesn't really work with Cartesian. Great. What else? Well, we saw that if you're dealing with a preorder, this forms a Cartesian category. Great. Well, if you're dealing with a preorder, you can also have a join. This is a coproduct in a preorder category. Not in a partial. In a partial order, it's strict, but in a preorder, it's not strict. Okay, let me just give you one last example and we'll talk a little bit about these things. Complex vector spaces. Okay, turns out that this V plus W is not only a product, but also V includes into W, V cross W plus W, and W includes into it. And so those are inclusion maps and they satisfy universal properties. So V plus W is not only the product, but it's a coproduct. And we're going to see this in several places, abelian groups, et cetera, where the product is equal to the coproduct. Very nice. In all of these cases, okay, in all of these cases, there's both a Cartesian product thing and a Cartesian. There's a Cartesian product and there's a Cartesian coproduct. We talked at the end of chapter 3 of what happens when you have both of these structures. Is there some type of isomorphism? Distributive, does the product distribute over the coproduct? Does the coproduct distribute over the product? Okay, so we call that, sometimes it works, sometimes it doesn't work. We call that distributive categories. We're not really going to deal with that a lot. Okay. Okay, so let's just recap. Section 5.2, we saw two types of monoidal categories, Cartesian categories, co-Cartesian categories. Okay, and the main point is they're more complicated. You have to worry about associativity, you have to worry about the unit, you have to worry about the braidings. But there are rules of how they behave, and we're going to generalize this all in section 5.3 when we just talk about, ready, monoidal categories. So far we had strict monoidal categories, then we had Cartesian categories, and now we're going to come, section 5.3, we're going to talk about monoidal categories where we have no, they don't necessarily come from a product, but they have to satisfy certain requirements, and we'll talk about those requirements. And that's the beginning of coherence theory, and that takes care of that. Okay, have a wonderful day.